Now we're going to look at parametric equations. Parametric equations are a set of equations of the type that we see here, where you have x is a function of t, f of t, and y is also a function of t, g of t. T here would be the parameter. So x and y are both functions of the parameter t. An example of where you'd use this type of thing is where you have equations for an object moving in a plane, or that is moving in a flat surface. So you have x and y coordinates for something, and these would both be a function of time. So t, in that case, the parameter would be time. For example, you may have seen this before. If you had x and y and you were looking at the equations for an object under gravity, where you get a parabola, this would be like if you throw a ball into the air and it follows a path like this through the air. The way you'd work out this curve is that you'd have an equation of motion in the x direction and an equation of motion in the y direction. You'd solve them both separately, so the y direction would have an initial velocity and then gravity acting against it. The x direction would just have a constant velocity. You'd get an equation for x as a function of time and for y as a function of time. You'd put them together then to get y as a function of x. In this case, the x velocity would be equal to dx dt, and the x acceleration would be equal to the second derivative, d2x dt squared. So, in physics, when you're solving this thing, you'd start with an equation for d2x dt squared, and you'd solve for x as a function of time. You do the same for y. You get two functions of time, and then if you want to know the actual path of the object through the air, you'd have to put together x and y. For each value of t, you get a value of x, value of y, and you'll put them together to make this graph. As an example, let's say x is equal to cosine of t and y is equal to sine of t. Our equations for x and y as functions of t. And let's try and plot this out. Y is a function of x. So let's make a table. We'll say t x is equal to cosine of t and y is equal to sine of t. When t is 0, cosine of t is 1, sine of t is 0. Next I'm going to pick t is equal to pi over 2. You'll see why in a minute. That gives me 0 for cosine and 1 for sine. T equal to pi gives me minus 1 and 0. 3 pi over 2 gives me 0 and minus 1. And then 2 pi gives me back to 1 and 0. So let's plot these with just x and y. So with t equal to 0, we were at point 1, 0. X equal to 1, y equals 0. Here. At t equal to pi over 2, we were at 0, 1. Here. At pi, we were at minus 1, 0. And then we were at 0 minus 1. And then finally we actually came back here. Now if we were to put in more values for t, values in between the ones I gave you, you'd find that we actually trace out a circle. In this case it's just a unit circle, right? It's a circle centered at 0, 0 with radius 1. And at every point along here, along this circle, in this case the angle here will actually be t. and the x value everywhere will be the cosine of t. The y value will be sine of t. So that's the unit circle. You've probably seen that before. I think it's in the maths table somewhere. So this unit circle is a useful thing for figuring out values for sine and cosine. Another example. Let's say x is equal to 5 times cosine of, I'm going to write omega t this time. Omega here is just some parameter, just some number. We're not saying what the value of it is for the moment. And let's say y is equal to 5 times sine of omega t. Now you can make a table of values like before, t, x and y, and then you can plot the x's and the y's together. And if you do that, what you'll find is this: x and y. When you let t equal to 0, x is going to be equal to 5 times cosine of 0, because, well, omega times 0 is going to be 0, is 5. And y is going to be equal to sine of 0, which is 0, times 5 is also 0. So that puts us here at 5, 0. And as we go around, as we increase t, you'll find that we actually trace out another circle, this time of radius 5. And as we keep increasing t, we'll just keep going around this circle. And so the value of omega here actually doesn't change the size of the circle or anything. What it will change is, as you increase t, how fast do you go around. You might notice now that we've actually rewritten a function that we've looked at before. There's the circle of radius 5 centered at the origin. We wrote it explicitly as y is a function of x. We wrote it implicitly with an equation involving x's and y's. And now we're looking at it again parametrically, where the curve is defined by two functions, a function for x and a function for y, both functions of a new parameter t. So how do we calculate dy dx? Well, think about the chain rule. With the chain rule, we could say that dy dt is equal to dy dx times dx dt. So the derivative of y with respect to t should be equal to the derivative of y with respect to x times the derivative of x with respect to t. Remember that x and y are both functions of t here. But implicitly also, you should be able to get y as a function of x and calculate dy dx. So the chain rule should give us this. We can rearrange that to say that dy dx should be equal to dy dt divided by dx dt. So I've divided both sides of that top equation by dx dt. So if I calculate dy dt and dx dt, then I can divide to get dy dx. So let's go back to what we had before. X is equal to 5 cosine omega t. That means that dx dt is equal to 5, and by the chain rule, the derivative of cosine will be minus sine, and then we multiply the whole thing by the derivative of what's in the brackets, which is differentiate omega t with respect to t, and you're just left with omega. So that's in brackets there. So it's minus 5 omega times sine of omega t. What about y? Y is equal to 5 times sine of omega t. dy dt, the derivative of this with respect to t, is going to be 5 times cosine omega t times omega by the chain rule. That's 5 omega cosine omega t. Finally, let's divide one by the other. So dy dx is equal to dy dt divided by dx dt is equal to 5 omega cosine omega t divided by minus 5 omega sine omega t. That's equal to 5 times cosine of omega t minus that divided by 5 times sine of omega t. Which, if you look at our functions for x and y, that's just equal to minus x over y. So that's the same answer we got before for dy dx. We got it both from explicit and implicit differentiation before, and now we have it again with the parametric differentiation. Another example, let's say we have x equals 5 minus t divided by 3 plus t, and y equals 3 minus t divided by 5 plus t. And we're asked to find dy dx at any point, and in particular at the point t is equal to 3. So how do we do this? First step, calculate dx dt and dy dt. Dx dt, so we calculate dx dt using the quotient rule. So the quotient rule is if we have u over v, well, if y is u over v, then dy dx is v times du dx minus u times dv dx over v squared. Here we're differentiating x with respect to t, so it's going to be by the quotient rule 3 plus t times the derivative of what's on top, which is going to be minus 1, minus the thing on top times the derivative of the thing on the bottom, which is just 1, all divided by the thing on the bottom squared. So that's the quotient rule. That's equal to minus 3 minus t minus 5 plus t over 3 plus t to be squared is equal to minus 8 over 3 plus t to be squared. dy dt is similar. By the quotient rule, right, it's going to be 5 plus t, that's the bit on the bottom, times the derivative of what's on top, which is minus 1, minus the bit on top, which is 3 minus c, times the derivative of what's on the bottom, which is 1, all divided by the bottom squared. That's going to be equal to minus 5 minus t minus 3 plus t divided by 5 plus t to be squared is equal to minus 8 again over 5 plus t to be squared. Now we put those together. We say dy dx is equal to dy dt divided by dx dt is equal to minus 8 over 5 plus t to be squared divided by minus 8 over 3 plus t to be squared. Now that's equal to minus 8 over 5 plus t to be squared times 3 plus t to be squared divided by minus 8. So we've divided by a fraction, so that's like turning that fraction upside down and multiplying. So dividing by minus 8 over 3 plus t to be squared is the same as multiplying by 3 plus t to be squared divided by minus 8, which gives me 3 plus t to be squared divided by 5 plus t to be squared. And that's fine as your answer for dy dx at any point. Then we were asked in particular at the point t is equal to 1.36, or no, t is equal to 3 implies that dy dx is equal to 3 plus 3 to be squared divided by 5 plus 3 to be squared is equal to 6 squared divided by 8 squared is equal to 36 over 64 is equal to 9 over 16. So that is parametric differentiation.